All right, let's get right into it. Picture this. Buried deep inside a mountain pass in Japan is one of the rarest pieces of technology on Earth. It's a train that doesn't just ride on the rails, it literally flies. This is the SC Maglev, a train that harnesses the incredible power of superconducting magnets to completely redefine what we think of as speed. But it also hides a really fascinating paradox.
I mean, just look at that number. 500 kilometers per hour. We're talking about absolutely mind-bending speed. That's fast enough to get you from Tokyo to Nagoya in just 40 minutes. Right now, that same trip takes more than twice as long.
And this is how it pulls it off. The train is literally hovering 10 centimeters above the track. There is zero physical contact. And what that means is you get way less friction, which means way less maintenance. It also means this train can run in pretty much any kind of weather. It is a completely revolutionary way to travel.
Which brings us to the big question, the paradox at the heart of all this. We have over 60,000 kilometers of regular high-speed rail crisscrossing the globe, and yet the only commercial high-speed maglev out there is a tiny 30-kilometer track in Shanghai. So why is this incredible technology so incredibly rare? Well, to figure that out, we've got to start with the science.
So how in the world do you float a train that weighs multiple tons? Turns out, it all comes down to magnetism. But there are two very different ways to go about it. The two main types of maglev are basically opposites. The first one, electromagnetic suspension, or EMS, uses electromagnets to pull the train up toward the track. That's the system they use in Shanghai. The thing is, it's inherently unstable. It needs constant computer adjustments to keep that tiny 8mm gap. If the power fails, the train drops onto the track. But the second method, the one Japan chose, is electrodynamic suspension, or EDS, and this system pushes the train up from the track using repulsive forces. And this is exactly why Japan went with EDS. It's what's called passively stable. If the train gets a little too close to the track, the repulsive force just naturally gets stronger and pushes it back up. No complicated computer controls needed. This is what allows for that huge 10-centimeter air gap, which is a massive advantage in a country like Japan that gets a lot of earthquakes. It just makes the whole system way more resilient. Now, there is a little catch with this pushing system. It only really kicks in when the train is already moving pretty fast. So until it hits about 100 kilometers per hour, the SC Maglev actually uses wheels that retract, kind of like an airplane's landing gear. So what's the secret sauce that makes this incredible pushing force possible? It all comes down to these superconducting coils. They're made from a special niobidium titanium alloy, and when you cool them down to ridiculously low temperatures, they can conduct electricity with zero resistance. That lets them create magnetic fields powerful enough to lift the entire train right off the ground. And of course, that immediately creates another huge engineering challenge. I mean, how on earth do you keep something at the temperature of liquid helium when it's on a train that is blasting through the countryside at half the speed of sound? The solution is honestly just genius. It's called a pulse tube refrigerator. It uses sound waves inside a sealed tube to create spots of high and low pressure. The high pressure makes heat, which gets vented away, but the low pressure spot gets intensely cold. That cold is then used to keep those superconducting coils chilled. It's actually the same kind of tech that James Webb Space Telescope uses to keep its instruments cold out in space. Okay, so we figured out how to make the train float. But actually building a safe, comfortable vehicle around these unbelievable forces, well, that is a whole other ballgame.
The biggest problem by far? Those same magnets that are powerful enough to lift a train would also cause total chaos for everything inside the cabin. We're talking pacemakers, laptops, even the magnetic strips on your credit cards. And you can't just block a magnetic field, so the engineers had to get creative and figure out how to redirect it instead.
To do this, they used a cool physics principle called magnetic reluctance. The easiest way to think about it is like electrical resistance, but for magnetic fields. Materials with low reluctance, like a special kind of steel, act like a copper wire for magnetism. They give the field an easy path to follow, letting you guide it where you want it to go.
So the engineers came up with this brilliant two-part solution. First, they used that special low-reluctance steel to basically build a shield that diverts the magnetic field around the cabin. And second, and this is the really clever part, they arranged the magnets on the train so that their fields cancel each other out, creating a safe, low-field bubble right where all the passengers are sitting. So, the train is floating, and it's shielded, but how does it actually move forward? The answer is basically a giant electric motor that's been taken apart, unrolled, and laid out flat along the track. Coils inside the guideway switch on and off in a perfect sequence, attracting and repelling the powerful magnets on the train, pulling and pushing it forward with incredible precision. This leads us to one final major engineering puzzle. For all the lights, the air conditioning, all the systems on board, you need power. But how in the world do you get electricity to a vehicle that has no physical connection to anything? Believe it or not, some of the early prototypes actually used a gas turbine generator, basically a jet engine on a train. But yeah, the final design is so much more elegant. It's using something called induction coils. As the train flies down the track, the rapidly changing magnetic fields from the guideway actually create an electrical current in these coils on the train, generating all the power it needs completely wirelessly.
So, we've seen the incredible science and the mind-blowing engineering, and now we can finally get to the heart of our paradox, the billion-dollar reality of actually building one of these things.
Just take a look at these numbers, because they pretty much tell the whole story. The French TGV, a super successful high-speed rail line, cost about $2 million per kilometer. Japan's own existing bullet train? Around $7 million. The new SC Maglev line? A jaw-dropping $77 million per kilometer. It's not even in the same league.
And this right here is the #1 reason why. See, to hit those insane speeds, the track has to be incredibly straight and flat. And in a place as mountainous as Japan, that means you have to tunnel. A lot. A staggering 86% of the track between Tokyo and Nagoya is going to be underground.
And here's the real irony. All of that tunneling creates a brand new problem. When a train traveling at 500 kilometers an hour enters a tunnel, it basically acts like a giant piston, compressing all the air in front of it. This creates enormous aerodynamic drag. So get this, the friction-free train is actually going to use 30% more energy than the conventional bullet train running on the very same route. So we have all the pieces of the puzzle now, an absolute engineering marvel that comes with a monumental price tag. Does it all add up? Is it actually worth it? Let's just break it down. When you look at pure raw speed, Maglev is the undisputed king. There's no contest. But when you look at construction cost and then at the sheer engineering complexity of it all, conventional high-speed rail wins by a total landslide. Japan is willing to pay that enormous price to shave about an hour off a supercritical travel route, but for pretty much the rest of the world, that trade-off just doesn't make any economic sense. And that really leaves us with this one last thought. Japan's SC Maglev is so much more than just a train. It's a statement. It's about pushing the absolute limits of what's technologically possible. And it forces us to ask a bigger question. For any great leap forward, what is the true cost? And what price are we, as a society, ultimately willing to pay for progress?